So these were the reactions that we had done for benzene in the last class. We had reviewed them, and we had talked about electrophilic substitution. All of them were electrophilic substitution. Most importantly, you had bromination, you had chlorination, and you had nitration of benzene. I mean, this specifically was known as this particular reaction was known as nitration. So we had done these reactions, and we had done acylation and alkylation as well, which will, I mean, this one is known as alkylation. And this one over here is known as acylation. So this is what was going on in the last class. We had actually this one. So in the last class, we had talked about benzene. We had talked about it having a delocalized electron cloud, which was evenly distributed. And then you had a bromination reaction where the bromine molecule would get polarized, but the polarization wasn't enough because the electron density on the benzene is not very high. So it's not able to repel the electron that much, which is why the positive charge and the negative charge on bromine is not very strong. And the positive bromine is not able to attract or pull the electron. So you need FeBr3 as a catalyst, which does the rest of the job, which polarizes the bromine molecule. The bromine positive comes in, borrows an electron from the available electron that the carbon has, and bonds with the carbon atom. The cloud on the benzene becomes partial. It gets a positive charge, and in the next step, the H is the one that loses the electron, and the electron cloud becomes complete again. But in this process, the H is lost, and it goes and bonds with the Br that was Br -1, and that was the mechanism for bromination. And then you had nitration, which was kind of exactly the same, except that in that case, nitric acid and sulfuric acid are reacted, and the NO2+1 nucleophile is created, and the NO2+1 nucleophile then goes, borrows an electron from the benzene electron cloud. It becomes positive as a result, and then the H gives away electron in the next step, and which is how the H is lost, and the NO2 goes and attaches to the benzene. So this was what we had done. Acylation was kind of exactly the same. That an acyl chloride, which is Cl bond O and Cl, it's got a positive carbon atom. So the positive carbon atom gets attracted to the benzene electron cloud and bonds with it. In alkylation, kind of the same thing. The carbon is positive, so the benzene electron cloud would be attracted to this particular carbon atom, not the other ones, but this one. And the Cl would eventually be lost. So this was acylation and alkylation, and we had started with electron donating groups, which were 2,4,6 directing groups. That you can have many things attached to benzene. You got arenes, which are benzene with a carbon chain. So methyl, 2 methyl groups, 1 methyl group, a propyl chain. You've got phenols. Phenols are benzene with an OH. So this one is 4-ethyl phenol because the ethyl group is on the 4th one. This one is known as 2,4,6 tribromophenol. Bromine is at 2, 4, and 6 position. So whenever you have benzene and it's got an OH, that's a phenol. And you also had phenylamines, which were benzene with an amine, benzaldehydes, nitrobenzene, you've got chlorobenzene, and you've got benzoic acid as well. So these are derivative compounds. So benzene is going to be attached to many things, and that would affect electrophilic substitution. So in arenes, you got two things. 2,4,6 directing groups are those where the groups have an electron donating effect. Basically what happens is that the carbon chain, it pushes electron density onto benzene. Same case over here. N has these lone pairs and oxygen also has these lone pairs. So the lone pairs, they overlap with benzene's electron cloud, like over here, and the electron density becomes greater at position 2, 6, and position number 4. So any electrophile would therefore be more attracted to positions 2, 4, and 6. So whenever you have OH next to a benzene, the electron cloud is no longer evenly distributed. What happens is the electron density becomes higher, greater on one side, and it becomes lesser at other sides because of the greater electrons on this side. All the other electrons, they get pushed to this one at the end. So it's very rare that the electrophile gets attracted to position 3 or 5. It's mostly be attracted to position 2, 4, and 6. And these were your 2 and 4, 2, 4, or 6 directing positions, groups. You've got NH2OH, amides, CH3, and Cl as well. Now, so this is the same thing, but remember that OH and NH2, they've got a large electron rating effect. You got an arene, the carbon chain has a very slight electron rating effect. So this 246 directing position thing is very prominent in phenols and phenylamine. The electron density on benzene pi electron cloud increases, and there's more attraction for electrophiles, and the benzene becomes activated because of the greater electron density. So there's going to be faster electrophilic substitution reaction. The bromine will be more attracted to a benzene that has an electron donating group attached to it. So in arenes, the conditions are the same as benzene. Alkyl chains have very slight electron donating effect, so slightly faster compared to benzene. Not much of a difference in benzenes and arenes. Kind of the same as benzene, except that bromine is going to get attached at position number 2 or 4. And the same with nitration. Same conditions, just slightly faster, very slightly faster, and then it will get attached to position number 2 and 4. But when it comes to electrophilic substitution of phenols, the lone pairs of oxygen overlap with benzene pi electron cloud, increasing electron density significantly. So in this case, the electron density is significantly higher now, and there's a much faster electrophilic substitution reaction. No catalyst is needed. So in this case, it's going to be a lot. So it's going to be a lot faster electrophilic substitution reaction because the electron density is really high. So the bromine electrophile would be very strongly attracted to it, and you'll get a fast reaction. Is this clear?
Yes, sir.
So then you've got, so it's going to be a lot faster electrophilic substitution reaction, and no catalyst would be needed in this case. So the conditions kind of change. So I'm going to add this to the chart that we were making. So I've got an alkyl chain here. So what I'm going to do is same thing with phenols. You get exact same electrophilic substitution reactions with phenols. Just let me. So we can talk about so we just complete the chart. So I've got a phenol, and what will happen is that there would be 3 reactions. All of them would be much, much faster. And for amines, it's exactly the same. So it's either phenol or phenylamine. Same thing. So you'll have a much faster reaction. So 3 electrophilic substitution reactions would happen. The first one is, so starting with so it's going to be 2,4,6. I mean, if you reacted with bromine, what will happen is that the OH or NH2, okay, I should have written or NH2. The bromines are going to get attached to all 3 positions. So there's going to be a bromine here. There'll be and the only conditions that are needed for this reaction are Br2 aqueous. That's it. No catalyst needed. Needed in this case. And this one is it's a white precipitate, often used to identify phenols. So it's used as a test for phenols. And then you have 2 other reactions. Nitration would also be much faster. So if you use dilute nitric acid, you'll still get nitration. So in dilute nitric acid, you're going to get 2 molecules. One is the OH or NH2 would still be there. And either you're going to have the NO2 at position number 2, or it's going to be present at position number 4. And the same goes over here. You're going to have so in this case, what will happen is, I mean, this is the other reaction. And in this other reaction, if you use concentrated nitric acid, so if concentrated nitric acid is used, then what will happen is that the NO2 will get attached to all 3 positions. So you have to remember the reaction of phenol. It's the same reaction as benzene, the same electrophilic substitution. Let me add that as well. These are all electrophilic substitution reactions. They all follow the exact same mechanisms. This one as well, that is electrophilic substitution. So all of them are electrophilic substitution. So all of them are electrophilic substitution, but except that phenols or phenylamine, let me add or to it. So phenol or amines, phenylamines. Exact same thing. Okay, is this clear?
Yes, sir.
Achha, फिर ये था कि what we did next was, achha, we talked about, I mean, this is all we already did. This was all about dilute nitric acid or concentrated nitric acid and phenylamine, pretty much the same thing. And then we started talking about, we did chlorobenzene, electrophilic going to be slow. Okay, that's fine. So what's after that? So then we did oxidation of arenes. Now, oxidation of arenes is simple. That whenever you have a carbon chain, no matter how big the carbon chain is, it doesn't really matter. No matter how big the carbon chain is, every time it's going to result in pretty much the same thing. I mean, the carbon chain, no matter how big the length is, it will simply turn into carboxylic acid. That's it. If it's got 5 carbon atoms, just replace it with a carboxylic acid. That's it. And then there's hydrogenation of benzene as well. So let's add that to the chart, both of these reactions. I'm going to add this to the chart as well. Just a second. So this one. We can add, let me make this bigger. So when you've got a carbon chain, you can turn it into a carboxylic acid. That is something that you can do. You can turn that. So you can turn that carbon chain. So let's copy this. And it will get oxidized to a carboxylic acid. It's going to get oxidized to a carboxylic acid if you heat it or boil it with KMnO4. And it's acidified and reflux. The other thing that's going to happen is that if you've got a carbon chain, what can also happen is, or what you can do is, if you react it with, if you do free radical substitution for this. So in free radical substitution, so that's your reaction with Cl2 plus. As it's Cl2 plus UV light. Now, in free radical substitution, if you use UV light, what will happen is, and it could be Br2 as well. So remember, UV light is the reaction of the carbon chain. So what will happen is that one of the hydrogens would get substituted in the carbon chain. So instead of having a carbon chain, it would be, I mean, it could be CH2, and there could be another CH2 and a Cl. So this is what can happen if you do free radical substitution. So remember this, that free radical substitution is not possible on the benzene ring. On the benzene ring, it's electrophilic substitution. For electrophilic substitution, you need a catalyst, or you need Br2 aqueous, like if it's a phenol. But if you want to replace one of the hydrogens in the carbon chain, that is going to be, what is going to be required is chlorine plus ultraviolet light. Is this clear?
Yes, sir.
Actually, just a second. So now the other thing is, you've got, so we did all of that, and we did the hydrogenation reaction. Like, you can turn a benzene into a cyclohexane by adding hydrogens to this thing. So what we can do is, I'll just Google. So this is cyclohexane. So we'll just so that's cyclohexane. So you can convert this into a cyclohexane. I mean, cyclohexane means it's a saturated molecule now. So we can do that. We can convert that into a cyclohexane if we hydrogenate this thing. And to hydrogenate this, it's going to be H2 plus a nickel catalyst. That is about it. So you'll get a cyclohexane, which is going to be a saturated molecule. So cyclohexane. So that's most of electrophilic substitution reactions that you should be aware of. And you should know the mechanisms of electrophilic substitution. The rest that we did was, and I'm going to fill those reactions as well over here. Just hold on 1 minute. Acha. इस पे आ जाते हैं. This is the next thing that we did. The other things that are important are comparison of hydrolysis of chlorine-related compounds. So you must know all of this. That the 3 types of chlorine-related compounds. We did the hydrolysis of these compounds. There's chlorobenzene, there's halogenoalkanes, normal halogenoalkanes, and then you've got acyl chlorides. So the first one is chlorobenzene. They don't have a hydrolysis. There's no reaction with water. And the reason is कि उसके पास पहले there's lots of electrons. It's got the benzene pi electron cloud, but plus the lone pairs on chlorine, they overlap with the carbon, with the benzene pi electron cloud. So there's a lot of electron density over here. So which is why any nucleophile, whether it's OH minus 1 or water as a molecule, the lone pairs of water or the OH minus 1 lone pairs, they're not even going to come close to it. So the lone pairs of electrons of Cl overlap with benzene's pi electron cloud. The CCl bond becomes stronger and has greater negative charge density. And the nucleophiles are going to be repelled. I mean, with the word nucleophile, I'm basically referring to water molecules. So you need to explain this. You need to explain that chlorobenzene has no hydrolysis whatsoever. Okay? Is this clear as well?
Yes, sir.
अच्छा, फिर ये कि what about halogenoalkanes? You've already done halogenoalkanes in your AS. So in halogenoalkanes, the conditions that are required are NaOH aqueous and reflux. Now for halogenoalkanes, now halogenoalkanes, what will happen is that you add the OH minus 1 nucleophile, and there is a reaction. Why? Because the carbon has a positive charge. So the OH minus 1 nucleophile is going to get attracted to it. And halogenoalkanes, the Cl reaction would be relatively slow and the I reaction would be relatively fast because this one has a weaker bond. Anyways, in AS, you studied two types of mechanisms. One was that you're going to have primary halogenoalkanes and they would have SN2 mechanisms. That's a primary halogenoalkane, the carbon, which has the Cl, the alpha carbon, is going to be bonded to just one carbon chain. And you're going to have tertiary halogenoalkanes, which would have SN1 mechanisms. Now, for primary halogenoalkanes, the mechanism involves a transition state. The carbon is very strongly positive. Why? Because the carbon is not surrounded by large groups. It's got hydrogens on both sides. So the positive charge of the carbon is really strong, which is why it's very hard for the Cl, which is polar, which is negative, to just go away. Because the negative Cl would be very strongly attracted to this very strong positive carbon atom. And because the positive charge is so strong, the OH minus 1 will also be very strongly attracted to this positive carbon atom. So what happens is the OH minus 1 comes in and that pushes the Cl away. So the OH minus 1 starts bonding and the Cl starts getting pushed away. And that is your reaction mechanism for this in this particular case. So that's an SN2 mechanism, which is one step. So why is a carbocation not formed? And the reason for that is that even if the Cl would like to take away electrons and the Cl would become negatively charged, it's not able to go away. Why? Because it will be attracted back very strongly because the carbon has a very strong positive charge. Why? Because it's not surrounded by large groups. So the positive carbon doesn't have a lot of alkyl chains. So carbocation has fewer electron-donating alkyl chains, hence it has a high positive charge density, which makes it very unstable, which means that it attracts the Cl minus 1 back again. So it's very hard to actually form the carbocation. So the only way to knock out the Cl is that the OH minus 1 comes in and pushes the Cl away. ठीक है, ये भी clear है? Is this clear?
Yes, sir.
Yeah.
So फिर ये कि what about tertiary halogenoalkanes? I mean, tertiary halogenoalkanes, they do like to form carbocations. The first thing is the positive charge is very small on this carbon. Why? Because it's surrounded by large groups. So even if there was a positive charge, lots of electrons around it, so that positive charge density would decrease because a lot of neighboring electrons would kind of neutralize it. So the positive charge on this carbocation is also very weak. So the Cl minus 1 could easily just go away and take away electrons because the positive carbocation will not be interested in those electrons because it can get electrons from elsewhere. Like the carbon chain over here is giving it electrons. The carbon chain over here is also. So on all sides, there are 9 electrons each. I mean, 9 electrons at the top, 9 over here, 9 over here. So the positive charge is obviously not going to be that large. So the next thing is, what's going to happen next? The carbocation, which is very stable, is formed. That's an intermediate. It's a carbocation intermediate. And the OH minus 1 then comes in. Why is the OH minus 1 not coming in first? Because it's not interested in this positive charge, because that's very small. And it's surrounded by large groups. So there's no way that the OH minus 1 could kind of come in and attack it. And it's also very small as well. So you wait for the carbocation to form, and then the OH minus 1 finds space and comes in. And so those are your two mechanisms for this. And you had both. Actually, you had both. This one is SN1 mechanism. So secondary halogenoalkanes have both SN1 and SN2 mechanisms. Secondary ones are the middle ones. And about this, you should also know about chirality and like if you have, and this is specifically, we wanted to talk about secondary halogenoalkanes, they can undergo both mechanisms. So if you have a molecule that's chiral, the mechanism, now this is the three-dimensional arrangement of an SN2 mechanism. Now, if you have a molecule that's chiral already, the carbon, the OH minus 1 always attacks from the opposite side. So the OH minus 1 always attacks from the opposite side because this side is negative. So when it attacks from the opposite side, the OH bonds with it, the Cl gets knocked out, but all the other bonds, they kind of flip, they get pushed to the right side. So there's always one type of chiral that's going to be formed, and which is this one. Because the OH minus 1 is always going to come and attack from the left side. So think of the OH minus 1 coming in, attacking this carbon atom, and the Cl getting pushed away. But all the other bonds kind of get pushed to the right. Compare this with the SN1 mechanism. Now in the SN1 mechanism, you've got a carbocation that is formed. And the carbocation is fan-shaped because whenever you have 3 bonds, then it is fan-shaped. And a fan is a planar molecule. So the OH minus 1 has two ways that it can attack. One is from the top, and the other one is at the bottom. Remember, in SN1 mechanism, the Cl goes away first, and the OH minus 1 comes in later. So which is why the carbocation intermediate is always fan-shaped. So the OH has got 2 options. So just like a fan, it could attach, come in, and bond from the bottom. And all the other bonds can get pushed upwards. Or it could attack from the top, and all the other bonds, they get pushed downwards. So both are equally likely. So both chiral carbon atoms are obtained. So in SN1 mechanism, the OH is always attacking from the left, and the Cl is leaving from the right side. But in SN2 mechanism, where the carbocation is formed, the OH minus 1 comes in later. So it could attach from the bottom or it could attach from the top, and both chirality are possible. Is that clear?
Yeah. Yes, sir.
So remember this about chirality, that both chiral molecules are possible in this case. So we'll continue tomorrow. My throat is really hurting at the moment. So just try and revise all of this.
Sir, so tomorrow we will continue this revision, or we will start another topic or something?
We'll do more past paper questions. I don't think we have done many organic past paper questions.
Yeah.
Okay, sir. Okay.
Yeah.
Okay, so thank you.
Okay.
Allah Hafiz.